Topic 4, Objective 2. Use long division to prove the remainder theorem and the factor theorem. So this objective will start our division of polynomials process. There's two types of division we're going to work with in this topic. Long division in this video, in this objective. And then the next video will be synthetic division. They play out a little bit differently, so I'm going to separate them into two different objectives. Now, before I start talking about division of polynomials, I want to go back to what it looks like to just divide numbers, alright? Because this remainder theorem and factor theorem that go hand in hand will probably be easily understood or easier to understand if I'm just working with numbers. It's the same process with just numbers as it is with polynomials of dividing. And the answers that you get will play out in the same way as well. Now, if I give you an example, if I draw a division box and I put the number 10 inside, that becomes my dividend. And if I want to divide 10 by 3, I put 3 on the outside, and that's my divisor. Now, the process of this is you got to think how many times does 10 go into, or how many times does 3 go into 10 evenly? Or if I look, I do always the first term divided by the first term, but in that case that doesn't work. 3 doesn't go into 1. So then I have to jump to the next term, which is 10 in this case. And I think 10 divided by 3 is 3. I know that 3 goes into 10 3 times. Then, in order to find how much is left over after I did that, I have to multiply 3 by 3, put my answer underneath the number inside the division box, and then subtract to find the remainder of what's left over after this. So 10 minus 9 is 1. So if I divide 10 by 3, I get 3 with a remainder of 1 over the original divisor of 3. Now 3 1/3 hopefully looks familiar to you. That is a mixed number or mixed fraction. And in this case, that should also tell you that 3 is not a factor of 10, right? And that should be pretty easy to understand because 3 doesn't go into 10 evenly, right? It has a remainder of 1. Same thing with polynomials. If you're dividing a factor from a polynomial and it gives you a remainder of a number or a piece left over, then it is not a factor of that polynomial. It's the same concept. Now let's do something that doesn't have a remainder. Something easy as well. Let's say I do 50 divided by 5. Same process, right? I know that first term, 5 divided by 5 is 1. I have to multiply back in there. 1 times 5 is 5. That goes underneath. And I subtract. In this case, it's 0. I bring down the next term. It's 0. And then I do division one more time. 0 divided by anything is 0. And so that answer goes up here. And I'm done. Right? I've worked with all my numbers inside the division box. And hopefully you know that 50 divided by 5 is 10. But I just showed you a quick version of long division with numbers. So in this case, 50 divided by 5 is 10. And it has no remainder. So I'll just put r equals 0. So when this is the case, if you divide something and it comes out as a whole piece without a remainder, then you should know that that is a factor of it, and that 5 is a factor of 50 because it goes in there evenly 10 times. Now it's the same thing with polynomials. If you divide a factor out of a polynomial and you get no remainder left over, then that should clue you that it is a factor indeed. So I'm going to give you two examples as you're doing this process of what your answer should look like. The first, x cubed minus 7. It could be any type of polynomial, but that's just an example I'm giving you. And then let's say this one has a remainder of a positive 2. Whenever you have a remainder, you put it over, like I did over here, I put it over the original divisor. And the original divisor will usually be a factor. In this case, will always be a factor. So that could be an example of an answer you come across, all right? And if you notice then, because after I did this division it has a remainder, then whatever factor I divided by, in this case I said that it's 2x plus 3, is not a factor of the original polynomial. And that'll make more sense when we try the process out. Another example you could have is just x cubed minus 7 with no remainder. If this is our final answer and it has a remainder of 0, then whatever factor I divided by of that polynomial is indeed a factor of that polynomial. Alright, so those are two types of answers you could get. One without a remainder and one with a remainder. And please note that if you do have a remainder, you need to either add it or subtract it. depending on if it's positive or negative, and put it over the original divisor. Alright, so with all that being said on remainders and comparing it to just numerical values, let's try one. Alright, I'm going to do example 1. Now please note, with example 1, it will, depending on what type of polynomial you get and what type of factor you divide by, the answer will play itself out differently. The process will always play itself out differently, so just be aware of that as you're going through this. I've put steps and I've listed them out as best I could to try to explain my thought process as I'm doing this, so please take it step by step as I do. And with division, I've always made note, please use side math if needed, so you can divide piece by piece and actually write it out. That really helps with this process as well. So, step 1 says to write in long division format. So right now it's saying that this big polynomial is being divided by this littler polynomial. In that case, it's potentially a factor of that big polynomial. So I'm going to label these quick. This is the dividend and the divisor. Alright? For my step 1 then, I'm going to draw a division box. Hopefully that looks familiar. And the dividend goes inside the division box, and the big polynomial goes in here. 7n to the 4th plus 11n cubed minus 30n squared. Now, I need to pause here and make another note, and I'm going to write this in blue. Do you notice, and if I was doing number 1, I would look at the powers. It needs to go in descending order, and all the powers in this process need to exist, okay? It goes from 4 to 3 to 2, but it skips over 1. It skips over the linear n term, right? There's no n to the first power. It just jumps to the number, or the constant, -2. And so because it skips over 1, I need to use a space holder, okay? So I'm going to put, and please make note of this, use space holder if needed. And again, you need a space holder if it skips over a power, right? Because that piece is missing, and that will kind of mess up the alignment of this process. So I'm going to always put plus, because it's just going to be a 0, and I'm going to put 0n. It's 0 because it doesn't exist, but I still need to write it there in terms of organization processes. And then finally, my -2. All right? So, coming up with the space holder, I'm done with step 1. I wrote it in long division format with the space holder. You won't always need a space holder, you just have to check to see the powers. Do they all, if it starts at 4, is there going to be a 4, a 3, a 2, a 1, and then the constant? If it skips over 1, then you need a space holder. Now, step 2, you take the first term of the polynomial divided by the first term of the factor. Oops, I'm not done with step 1. I didn't include my divisor. My divisor goes outside the division box. Haha, now I'm done with step 1. Alright, step 2. First term of the polynomial, in this case is 7n to the 4th, divided by the first term of the divisor, or the factor in question. So I can do side math. I did not leave myself a lot of room to do side math, but if I do 7n to the 4th divided by 7n, that gives me an answer of 7 divided by 7 is 1, and then n to the 4th divided by n is n cubed. Alright, we've worked with division before, so hopefully that is review for you. My answer that I get goes above the like term right here. The n cubed is inside the box, it goes above that like term, up above the box, alright? At that point, I am done with step 2. I wrote my answer above like term of polynomial. Now, step 3 states, multiply the answer that I just got with the entire factor. In this case, the -10 comes into play of the factor. And write the answers that I get below the like terms of the polynomial. So my answers in step 3, I'll put a little step 3 right here. This was step 2 down here. My answers of step 3 will go down here, below it, alright? Now, n cubed times 7n, and this is the math I'm actually doing. N cubed times 7n, I'll put it over here. N cubed times the factor 7n minus 10, alright? That's that math I'm doing, back and forth. And it would really help, I would really strongly suggest that you do this side math. I know it's tedious, but it'll help you be successful in the long run. N cubed times 7n is 7n to the fourth, and then n cubed minus 10 is minus 10n cubed. Now, you should notice, and I put a hint down here, when you do this multiplication and you write it below the polynomials, you should start to recognize that one of the terms should be the exact same as the above term, all right? 7n to the fourth is the same in this case. And then I'm going to put minus 10n cubed. So I've lined it up nice and neat. It's underneath each like term. And that is done with step 3. All right, step 4 says, and this is when we're going to start canceling stuff out. Division means you cancel stuff out, right? Step 4 means subtract the answer from the like terms of the polynomial. Hint, one of the terms should cancel out, all right? So, with step 4, and that's technically down here, but it's going to exist up here as well. I'm going to put parentheses around what I'm subtracting, and it's subtraction, all right? Make note that it is subtraction. I'm going to do 7n to the fourth minus, I'm going to put that minus in red. 7n to the fourth minus 7n to the fourth, and they cancel out. It becomes 0, all right? And this is my step 4, final piece of step 4. And then I go to the next term, 11n cubed minus a negative 10n cubed. That minus and that negative interact with each other and it turns positive. So that makes me get a positive 21n cubed. All right. That is the end of step 4. I subtract answers and I canceled something out. I got a 0 for 1. That means I'm on the right track, all right, because now I'm getting rid of pieces and my answer is going to be a smaller polynomial. Step 5 then says bring down the next term and repeat the process until there are no more terms remaining under the division box. So now it's just rinse and repeat. I'm going to drop down the next one, negative 30n squared. And then I can drop down the other ones as well, plus 0n and then minus 2. But they won't come into play till later, all right? But it might be helpful to actually drop down every piece after this. Now, it's the same thing. My first term divided by the first term. In this case, 21n cubed divided by 7n. In that case, it is 3n squared. That answer goes up here, and it's a positive 3n squared. Please put plus if it's a positive. All right, then step 3 says multiply the answer with the entire factor and write the answer below the like terms. 3n squared times 7n is 21n cubed. And then 3n squared times negative 10 is negative 30n squared. Remember, that's this process. I just did this process again, but I used my next answer piece that I had. All right? So I did 3n squared times 7n, 3n squared times negative 10. Now, that is done with step 3. I move on to step 4. Subtract the answer from the above polynomials like terms. Hint, one of them should cancel out. Sometimes more will. But in this case, 21n cubed minus 21n cubed is 0. They go bye-bye. Then I have a negative 30 minus a negative. It turns plus. They also go bye-bye. So I am left with zeros in this case. I bring down the next terms, which in this case, there's a 0n squared that still exists, and then a minus 2. Now this problem I'm showing you is unique because I can't do any more division, all right? 7n doesn't go into 0, 7n doesn't go into negative 2. So my final answer will include this as its remainder, and this is where your answers will look different depending on the polynomial. But my final answer is n cubed, I'm getting it from up here, plus 3n squared minus the remainder of 2 over 7n minus 10, the original divisor. And that should tell you two things, all right? The fact that this factor in question had a remainder when I divided it, it is not a factor of this big polynomial here, all right? And the solution of that factor is also not a solution of that polynomial. Go ahead and pause this video and try the you-do problem on your own. Here's the work I did for number 2. Please check your work with mine. I discovered that my answer was p squared plus 10p, so the factoring question